So I have some homework. I wanted to let you know some of you only got partial credit on 3.5 because it was talking about using Venn diagrams, and if you didn't draw a Venn diagram to represent whether things were valid or invalid, then I gave you half credit. Now if you want to return in 3.5 again with the diagrams when they're appropriate, so a lot of people didn't do that. Likewise on section 3.3, there were truth tables that needed to be done, and a lot of times people didn't do the truth tables, so I can't give you full credit there either. Pardon me?
When do you put these on Blackboard?
When do I put what? The homework grades? I usually just put the final grade. I don't put the individual assignments that are due. So if you need to know which ones you haven't turned in, then you can ask me and I'll let you know. Yep. So I'm going to do the homework first, and then I'm going to hand the test back. So if you're online.
So the last homework you guys do the table?
Pardon me? The last homework, 3.6, you would have to do a table. For 3.5 is where you should have done the Venn diagrams. So a few people did do the Venn diagrams where you draw the circle, then you draw the circle inside the circle, and then that whole process. Pardon me? Yeah, you can redo it if you want to get full credit for that homework. You probably watched the video and wrote the answers down. So if you want to, I'm sure I did some kind of drawings to explain how they work. Likewise, anytime there's truth tables in homework, you can't just say the answer is whatever, because you just at least see you've done something you've written out. So yeah, 3.6, you're supposed to use truth tables to show whether an argument is valid or not. So you need to show the truth tables, which can get fairly big. Okay, so let me tell you about the test. So there were a total of 204 points. I did curve it somewhat. So your grade is in the center, and if you have any questions about why I took points off, they're not all the same. So the truth table ones are counted more points, and the Venn diagrams where you had to put numbers in. So the last problem and the 8th problem were worth more points. I went through your Venn diagrams to see if you made an error to begin with, but then did it correctly after that, then I gave you credit for it. So I tried to give you as much credit as possible. I must have done a better job explaining Venn diagrams in the other class. You guys did okay on the truth tables. The Venn diagrams are not so good. If you're listening online or listening to the recording, you can come by. I'll bring you to class next time, but if you don't come to class, then physically, you can stop by my office, or I'll give them to you in the next test, whichever way you want to do it. So you did do okay. What's that?
Generally, it either looks foreign or
Guess that's everybody here. I don't see anybody. So the highest grade on the test was 100, so that was good. It was a 90 set. Yeah. Oh, you were worried? Here, Justin, hold on. Well, you know, on average you do, but if you did well, then it doesn't mean that everybody did worse. It just means that some people did worse. It was at least a half a letter grade, I think, maybe even a little bit more. So let me just look through here if there's anything to tell you. So number 6, if you didn't say if they were equivalent or not, it asked you to determine whether they were equivalent, and so just writing out the tables without making a comment was not sufficient. They were equivalent, so that was the answer. I thought I talked about this in this class. Maybe I didn't emphasize this as much, but on problem number 8, a fair number of people forgot to subtract. When they looked at the intersections of two sets, they forgot to subtract the 4 people that were in the middle section. So you should have had 4 in the little middle shield area. And for example, there are 7 in the intersection of A and C, so some people put 7 in that one blank spot instead of subtracting 4 from 7 to get 3. Pardon me?
What would be like B?
Oh, what would the numbers in be? I didn't bring my solution, but let me see if I hear somebody. Okay, so B would have been 7 in the bigger section. And then if you go counterclockwise, it'd be starting with 7, 7, 4, 5. And there were 11 that were not in any of them. And in the last problem, so the 4 spaces that were in sets Taylor, there were 41 people that only liked Taylor, there were 16 people that only liked Ed, and there were 21 that only liked Katie. Those are in the outside parts. Then you have 5 that everybody liked. And then in the little other parts of the football, so there were 7 that liked Taylor and Katie but didn't like Ed. There were 6 that liked Ed and Katie but not Taylor. And there were 12 that liked Ed and Taylor but not Katie. And there were 9 people that didn't like any of those 3. So yeah, if you made an error on number 8 incorrectly, you probably did number 16 wrong. Some people forgot to answer the 2 questions after filling out the diagram. Okay. So we are moving on here. So we are on chapter 9. We were talking about vertical angles. So you create 2 vertical angles. Well, you create 4 angles when you have 2 intersecting lines. And the opposite angles opposite each other are called vertical angles. So this angle here and this angle there are vertical angles, and this angle here and this angle there are vertical angles, and the pairs of vertical angles are equal to each other. So we have this problem, which I guess we didn't solve because I don't see an answer. You have a couple of problems that use the fact that vertical angles are equal to each other to create an algebraic equation that you solve using algebra. So this particular problem, or did I do it? Let me see here. No, I didn't. Nothing there. So in this particular problem, because we have two intersecting lines, these two angles are vertical angles. And as a consequence, they are equal to each other. So you would, to solve this problem, you would say 4x plus 19, which is the value for this angle, is equal to 6x minus 5. So that's how we use the information about angles. And at that point, it's an algebra problem. So you want to solve for x, so we subtract 6x from both sides so that we get all the x stuff on the left-hand side, and we subtract 19 from both sides to get all the constant stuff on the right-hand side. So when we add these two numbers together, 4x plus a negative 6x gives us a negative 2x. This plus that gives us 0. 6x plus negative 6x is 0x. And negative 5 plus negative 19 is negative 24. And we can simplify that down to negative 2x equals negative 24 by just dropping the terms that are 0. And then you divide by negative 2. And you get x is equal to 12. So that's the value of x. There's always a few people when they do this problem on the test, or one like it, is they think that's the answer. But the answer is, what is the angle that satisfies this? So we have one more step. We can either use this equation or we can use this equation to solve for the angle. And we should get the same answer either way, because that's what we initially did to solve the problem. So I'm going to choose this one. So we basically want to evaluate 4x plus 19 when x equals 12. So you put 4 times 12 plus 19. 4 times 12 is 48, plus 19 is 67 degrees. So this angle is 67 degrees, and this angle is 67 degrees. If you plug x equals 12 into there, you get 67 degrees. You get 6 times 12, which is 72, minus 5, 67. So it doesn't matter which equation you use. The key thing is that these two angles are equal to each other. The other thing we mentioned, I think, was that the two adjacent angles, when you create these four angles from the intersection of two lines, these two add up to 180, these two add up to 180, those two add up to 180, and those two add up to 180. So pretty much all these problems, the angles either add up to 180, most of the problems add up to 180, or they equal each other. And typically they show them where you have one angle that's larger than the other angle. So this one is an obtuse angle, which is greater than 90 degrees. This one's an acute angle, which is less than 90 degrees. So the small angles equal to each other, and the big angles are equal to each other. The small angle plus the big angle equals 180 degrees. So you can just do it on, you don't even have to memorize equations, just think about, small equals small, big equals big, small plus big equals 180. So what I just talked about, those two adjacent angles are created because you have one line that's cut by another line. And if I extend it, so these are two lines. So this is just one side of two intersecting lines, just to show you it's the same thing. And so we have two adjacent angles, and because of that, the two adjacent angles add up to 180 degrees. We call those two angles, they're supplements of each other. So we'll work the problem in a second. Let's just say a few things about supplementary angles. Supplementary angles are angles whose sum is 180 degrees. So if I said, I could say 63 degrees and 117 degrees are supplemental angles, because they're add those numbers together, you get 180. I'm not showing them on a graph or on a figure. They don't have to be adjacent to each other. The only requirement is that supplemental angles have to add up to 180 degrees. So as a but when you have a straight line with a ray extending off of it, the two angles that are adjacent to each other are supplemental. Just because when you have adjacent angles, the total angle is equal to the sum of the individual angles. So, using that fact in this drawing, we can solve the problem, again, by asking the question, are these two angles equal to each other, or are they equal to 180? Sum is equal to 180. Well, one's big, one's small, so instead of setting these equal to each other, we're going to do the other thing, the other option. And so we're going to have 3x minus 30 plus 4x equals 180 degrees. So that's the geometry. The rest of it is algebra. So 3x plus 4x, that gives us 7x. We have the negative 30 hanging out there. We need to isolate the variable term, so we're going to add 30 to both sides. So 7x plus no x is 7x. Here you get 0. Here you get 210. You can drop the zeros or the 0x's, and then you divide by the constant that's in front of the variable. That 7 divided by 7 is 1. So we get x, and 210 divided by 7 is 30. So x is 30. That's not the answer. The answer is either 30x minus, well, actually, we do have two angles here, so we have to calculate both of them. They're not equal to each other, so we have to do both of them. So this angle is going to be 30x minus 30 when x equals 30. So we get 3 times 30 minus 30, which is 90, minus 30, which is 60. So this angle is 60 degrees. And the second angle, there's two ways you can do it. You could use the equation for x when x equals 30, which would give you 4 times 30, which is 120. Or you could just say, well, if this is 60, then this has to be 180 minus 60, so the sum. So it's either way. We could do that way, or we could say this angle here is 180 minus the other angle, which is still 120. It's the same. So the key thing to remember here is when you see these problems, solve for x, which most people get right, but once you solve for x, plug x back into the equations. If they're equal to each other, you only have to do it one time. If they're not equal to each other, then you have to get the two numbers. And you can always check to make sure they're true, correct answers by adding these two back together, checking your answer and seeing it's 180 degrees. Okay, the other kind of angles are complementary angles. And what complementary angles are two angles. Let me move this down out of the way. So we'll write the definition out. Two angles whose sum is 90 degrees. So in this drawing, we have a right angle here between these two perpendicular lines, and so we know that this angle, whatever it is, I'm going to make up a problem here, so hopefully it works out right. 3x minus 5, and this one's going to be 2x plus 10. So the sum of these two angles has to equal 90 degrees. So if I were to solve this problem, instead of saying they add up to 180 or they're equal to each other, this is the one special case where it's different and they add up to 90 degrees. So to solve this problem, what is x and then what are the values of the angles? I would say 2x plus 10, which is the measure of this angle, plus the second angle, which is 3x minus 5, has to add up to 90 because they are complementary angles. So to solve this, we would add the two x terms together. 2 plus 3 is 5, so we have 5x. And we have 10 minus 5, which is 5. So I've just simplified. Remember algebra, you combine like terms. So that's the first thing we've done. Once we've combined all the like terms, then we want to isolate the variable term on one side. So to do that, we subtract 5 from both sides. So you'll get 5x plus 0 is equal to 85. So 5x equals 85, and x is equal to some decimal number because I made the problem up, so this is okay. We'll get our calculator out. Here's a rule that we'll learn in the second semester, but I'm going to tell you now because then when you see it next time, you'll remember it. There's a trick to know whether you can divide numbers by 3. Well, actually, you can divide that by 5. I was thinking of 3, so I won't tell you the trick yet. So actually, it's going to give me a whole number, 17. So actually, x is a number, but it's not. I should have figured that out because any number ending in a 5 or a 0 can be divisible by 5. So I was subconsciously thinking this was a 3, and that's why I was confused. So we solve for x, and therefore we have two angles. We're going to have the first angle is 2x plus 10 when x equals 17. So we get 2 times 17 plus 10, which is 34 plus 10, which is 44. So this angle is 44 degrees. And the other angle, we know just because it's a supplement, is going to be 46 degrees. So the two ways of getting the second angle is to take 90 minus 44, which is 46, or evaluate the second equation when x equals 17. So we get 3 times 17 minus 5. 3 times 17 is 51, minus 5 is 46. So either way, you get the second angle. Okay, so what we talked about is the intersection of two lines creates 4 angles. The opposite angles are called vertical angles, and the vertical angles are equal to each other. The adjacent angles add up to 180 degrees. What else do we find out? Supplemental angles are two angles that add up to 180 degrees. Complementary angles are two angles that add up to 90 degrees. Okay, and this is something, okay, you're leaving. What are you doing? Okay, okay, yeah. She's abandoning me. I feel rejected. Okay. Parallel lines. So parallel lines, it's kind of like defining lines. What are parallel lines? Well, parallel lines, for one thing, is they have to be in the same plane. So they're aligned like this. Yeah, so without using lines, I know I'm sorry. It's too complicated to define a line. You know what a line is, right? Yeah, you do. Well, no, I'm not going to do that. We're going to assume. We looked it up. Didn't we look that up the other day online? So that's we have parallel. What do they say? Parallel infinitely extended one-dimensional figures with no curvature. Parallel lines. No, I'm just kidding. We don't need to know that. I'm just pointing out that sometimes math definitions are so complicated, but we at least, there are sometimes what we know just from using it so many times is probably better than trying to come up with some complicated expression. Okay, everybody knows what a line. Now there are other cases where there are things that we think we know but we don't know. That's called physics. People have preconceived notions about how physics works because they live in a world that the laws of physics apply, and they come up with certain conclusions about what those laws are, which are incorrect. So when you try to teach them physics, they revert back to what they've learned by experience, which is all wrong, and so it's hard to break people of that. But for lines, I think we can assume that everybody's understanding of what a line is. If you made it to Dabney, you probably know what a line looks like. So the key thing here is that these infinitely extended things with no curvature, things like that, one-dimensional, yeah, they do not intersect, okay? From an algebra standpoint, we would say they have the same slope, so lines of the same slope never intersect. One thing that people get confused about is, or at least they probably don't even think about it, but if you have two lines like this one going this way and that going that way, they don't ever intersect, but they're not parallel lines. Parallel lines have to be in the same plane. So these are called skew lines, and this is a parallel line. Okay. The key thing is parallel lines never intersect. So then what we do is we create this thing that you remember from geometry, probably with disdain. So you have two parallel lines with the transversal. So the transversal is any line that's not parallel to the original two parallel lines, because at some point they're going to intersect. So because these two lines are not parallel, they intersect somewhere, and these two lines intersect. And there's a lot of interesting stuff that you can use to, if you can either have this happen in real life, or you can create a line in sort of fake life and answer geometry questions. I'll give you an example later, but just take my word for it right now. So basically what we have is we have two intersecting lines, and here we have two intersecting lines. So we've already talked about that. So what we know from that is that, let's say this angle has some value, then this other angle, which is immediately opposite the point of intersection, also has that same value. Because these two lines are parallel, we can also say that these two angles here also have the same value as what's on the other parallel line. So all of these angles have the same value, whatever they are. And again, just thinking about big versus small. So when you have two parallel lines and a transversal, all the small angles have the same value, and all the bigger angles have the same value. Now you might get a case where, you're like here, very close to, if you're there perpendicular, then they're all the same. They're all 90 degrees. But sometimes you might get a drawing that looks like that. But again, this one is slightly bigger than that one. So even though it's, this is small and this is big, they're pretty close to each other. But again, all the smaller angles are equal to each other, and all the bigger angles are equal to each other. So we'll redraw my line here. Hopefully get it where it was originally located. Okay, so I'll show the other angles just by showing two little things. Now, all these angles and the specific relationship between the angles have special geometry names. I'm not going to ask you to memorize them. This is just a review. You probably have forgotten what they are by now, because it's been a while since you've taken geometry, but it may come back to you and like, oh yeah, I remember that. So here we have the two parallel lines and the transversal. this angle, which is a big angle, and this angle, which is also big, they're on opposite sides or alternating sides of the transversal, and they are inside the two parallel lines. So as a consequence, we call them alternate interior because they're interior. And because they're both big, the rule is the angles are equal to each other, which is what we said. Okay. The other large angles that are here and here, or down here, which is there and there, these are called alternate exterior angles. Again, they're on all the alternate sides of the transversal, and they are exterior to the two parallel lines. They're both big, so they're both equal. They're equal to each other. Then you have the other cases where they are, well, this case. So what these are called are interior angles on the same side of the transversal. That's a mouthful. So they're on the same side because they're both on this right side. And in this case, because one's big and one's small, they add up to 180 degrees. So that's the rule. And then finally, corresponding angles are on the same side and they're the same size. So this one's exterior, this one's interior, but they're on the same side of the transversal, and so they're corresponding. It's almost like a similar triangle kind of thing. They're in similar positions relative to the transversal and the parallel lines. Because they're both small, they're both equal to each other. So that's all. You don't have to remember all these. You don't have to remember for an alternating, internal, whatever it is, the angles. I can't remember the rule. The only rule you have to remember is big equals big, small equals small, and big plus small equals 180 degrees. That's it. That's all I remember. I didn't, I got degrees in engineering, and I didn't have to use words like this. So I think. What's that? Yeah, that one's a lot of words to describe it. So you have a similar kind of problem where you got to solve an algebraic equation, and I left off part of it, so I'm going to have to find the problem in the book. So I'm ready for the final debate tonight, I think. So here's an interesting thing I read, okay? The WikiLeaks thing. So, and I don't know if this is true or whether this is something that could happen. So the way you handle WikiLeaks, especially if you're trying to take advantage of it, like the Russians, to cause confusion in the U.S. election and hire, or not hire, but vote for Putin's buddy. What you do, and so what you do is when you leak the first information, so you don't leak it all at one time, you leak some initial information, and you leak it so that it's true. You leak it as an exact, so they cannot deny that that was true. And then you send out another leak, and that one's true. And so people start to believe that every leak is true. Then you get to later, and then you start making changes to the emails, which they aren't true. So then everybody thinks, well, the first two were true, so therefore it's using what do you call it, inductive reasoning. You do a few that are true, so you assume the next one's true, and by the time they get around to proving that the third one actually is false, the election's over, and you've done some kind of subversive. Yeah, it's hard to defend against, which is really scary. I mean, it's very scary to think about that somebody could do that, especially your adversary, who is Russia. So you have to think about, do you ever never send emails anymore because they might get hacked? That's another interesting thing. I heard that Marco Rubio said, you guys should ignore these WikiLeaks because we could be next. So don't get too excited and gloating over all the good things we're able to make the Democrats look bad, because equally likely it's kind of like Donald Trump, you know, laying into Clinton about the,
How was she doing her email? Was it through an encrypted key?
well, the emails that are leaked right now are from her campaign manager.
The way you do this properly is you have a key. The person you're talking to.
Yeah, I'm not sure how they. Well, I don't think they're not intercepting the emails as they're sent. They're going into somebody's email box and then downloading all of it. So the encryption would not work in that case. So it only works in when you're transmitting. Anyway, back to the. Yeah, I don't know that. I don't know who does the Democratic Party. But it's it's a whole set of new bad things. Okay, so in this case, they give you these two angles, and all you have to do is say, are they equal to each other, or do they add up to 180 degrees? So because this is a large angle and this is a large angle, we know that to solve the problem, you just set them equal to each other. So we get the algebraic equation we need to solve. So we subtract 6x from both sides, and we subtract 61 from both sides. So 2 minus 6, or 2 plus negative 6 is negative 4. Positive 64 minus 64 is 0. 6x minus 6x, or 6x plus negative 6x is 0x. And negative 51 minus 61 is negative 112. So we then remove these. You don't have to include those if you don't want to, but I'm always surprised at how poor people's algebra skills are. So we cover algebra review in the second semester. I'm like, oh my God, this is awful. Where'd you go to? These guys go to high school. Okay. So you solve for x. X is not the answer, right? X is almost the answer. So we have to go back and we have to plug in. So either one, because they're equal to each other, we only have to do it one time. $28. So we're going to substitute that in. So we get 2 times 28 plus 61, which is 56 plus 61, which is 117. So that's 117 degrees. So, you know, this is 117 degrees. This is 117 degrees. This is 117 degrees. This is 117 degrees. All the other ones are the supplement of this number. What do you have to add to 117 to get 180? How many people do it in their head? Kinsey left. She knows how to do things. 63. So if that's 63 degrees, that's 63 degrees. That's 63 degrees. That's 63 degrees. All the big angles are equal to each other. All the small angles are equal to each other. Okay, do one more. This is the other case. So this is pointing towards the small angle. This is pointing towards the big angle. And it really doesn't, I could point to any big angle or any small angle because they're all the same. So in this case, we would say, instead of them being equal to each other, it's the other option. Big plus small equals 180. So we have x plus 1, which is a small angle, plus the big angle is equal to 180. So we combine like terms. 1x plus 4x is 5x. 1 minus 56 is negative 55. We add 55 to both sides to get 0. And there you would get 235. So 5x equals 235. Divide both sides by 5. And I get x is equal to, oh, by 5. I divided by 4. 47. Again, that's not the final answer. The final answer is, for the small angle, is x plus 1 when x equals 47. So 47 plus 1 equals 48. So this angle is 48 degrees. Therefore, this one is 132 degrees. They have to add together to be 180. And then likewise, all these other ones. This is 132, this is 48, 132, 48, 130, no, 48. $132. What we're trying to get to, let me see if I can find it. Let me save this. Save. Is I'm going to give this to you on the test. We're going to have two parallel lines with all these transversals. And we have to figure out what, given these three values, what are the values of every other angle on this drawing? So we've learned about half of what we need to learn. One is that, you know, this angle, this is 45, so that's 45, that's 135, that's 135. Likewise here. The second part that we have to deal with is triangles, and we'll do that in section 3. But that's what we're trying to get to something a little more complicated. So the homework for this section is there you go. One interesting thing about debate tonight is the moderator is a Fox anchor. But he's probably the most, yeah, I don't know if I want to use that word, but he's probably the most reasonable. It's Chris Wallace, whose dad, Mike Wallace, used to be a very, he's one of the first guys on 60 Minutes so it'll be interesting to see what kind of questions he asks, because you can think of it. He might say he's going to be favorable towards Trump because Fox News is, but because he is somewhat reasonable, he may actually, to prove that he isn't biased towards Fox News, that he may actually throw some pretty hard questions at Trump. So it'll be interesting to see which one of those turns out to be. Yeah, party-wise, yeah. Okay, so we're going to move to section 2 here. So section 2 is a lot of definitions of different kinds of curves, polygons, circles. So we're going to move fairly quickly through this. It's a lot of definitions that you've seen before, and I'll stop where I think it's important, but like I said, it's kind of a review. You've probably forgotten some of these things, but we're not going to spend enough time for you to memorize them all. We wouldn't want you to do that anyway. So I would suggest just paying attention. You don't need to write any notes. That way I can move faster and get through it. Section 3 is more interesting. Okay, so in section 1 we talked about lines, which were whatever that definition was. And we talked about angles, which were two rays. So to get a little bit more complicated in geometry, you have curves which are not straight anymore. They're not infinitely extended, one-dimensional, whatever they said. What did they say? I can't forget. Infinitely extended, one-dimensional figures with no curvature. So in this case, curve, as the name implies, has some curvature to it. So a simple curve is just something you would draw with your pen without picking it up. Okay, that's a curve. Make sure I don't draw anything rude. I don't know what that is. That's somebody with a finger like that. Okay, so that's a simple curve. So it has curvature to it compared to lines which don't have any curvature. A closed curve would just be a same kind of thing, except you come back and the ends meet, so that looks kind of like a shoe, maybe like a slipper. Okay, so that's a closed curve. That's a simple curve. Now, in terms of the curvature, you can have what's called a concave or convex surface, and some of it's kind of relative. You know, if I draw this like that, just the curve and not the closed curve, if I look at it from this way, it's bowing outward. So it's convex if I look at it from that way, and if I look at it from this way, it's bending inwards. So it's concave. So it's all relative. So really, concave and convex has to be relative to something. In calculus, it has to do with, well, actually, we call everything concave. So, but here we're talking about some kind of shape. And so we're talking about if you had somebody looking from the inside to the outside like this. Okay. So is it bending? And actually, that's the wrong one. I need to move that down so you get confused. So this surface relative to this observer, my eyeball here, it's concave because it's bending in. Okay. Whereas if I had a curve like this, let's say went like this and then looked kind of like that, and I'm looking at, again with my eye this way, this would be a convex surface because it's bending away. Now, the most useful, where this is used a lot, is in lenses for glasses. So you can have a glass that looks like that, or you can have a piece of glass where it's thinner in the middle. So this is called a convex lens, and this is called a concave lens. So this is bending out, and this one's bending in. Okay, I'm not going to test you on that, but that's okay. So now, now that we're going to talk about other kinds of closed curves that are made up of straight line segments, and they're classified according to how many sides are in the polygon. So you have to have at least 3 sides, because if you just had 2 sides, you just have a flat thing. So you got to have 3 sides, this side, and then you got a third side. So the simplest polygon is a triangle. Then if you go to 4 sides, then you have a quadrilateral. And there are special cases of quadrilaterals, which we'll talk about: parallelograms, rectangles, squares. You know, depending upon the relative position of the 2 sides, all the sides, and the angles associated with them. But a general 4-sided polygon is a quadrilateral. Pentagon, you know, you think of the Pentagon, which is the, you know, in, was it in Alexandria? Arlington, maybe? it's a regular polygon because all 5 sides are equal length and the angles are all equal to each other. But a general polygon is just a shape that has 5 sides. And then you got a hexagon with 6 sides, heptagon with 7 sides, an octagon with 8, a nonagon, which is 9, and a decagon, which is 10. Okay. Again, I'm not going to ask you to memorize those names. Okay, now this one's the most important one because most important shapes either are triangles or they can be made into triangles. So they've got some special names, and these actually you do need to know, but you can look in your book and you can draw a picture on your cheat sheet to remind you what it is. So a triangle has 3 sides, and there's 3 special kinds of triangles based upon the angles. If all 3 angles are less than 90 degrees, then it's called an acute triangle. If one of the angles is 90 degrees, then it's a right triangle. And if one of the angles is an angle greater than 90 but less than 180, it's called an obtuse triangle. And then you can classify the triangles according to the equality of the sides. So a triangle that has all 3 sides equal to each other, which also has all 3 angles equal to each other, is called an equilateral triangle. A triangle that has 2 sides that are equal to each other is called an isosceles triangle. These 2 angles in the isosceles triangle are also equal to each other. And then finally, the one that has 3 different side lengths is called a scalene triangle. So part of your homework is just to recognize triangles by these characteristics. So here's a few examples just to kind of give you an idea what the homework's about. So here, what type of triangle do we have? They've given you numbers which really don't have anything to do with what kind of triangle this is. Well, I guess they do it to some extent, but they're not asking you to use the lengths of the sides to determine that. All you have to do is look at it and say, well, they've got this little square piece here, which means that's 90 degrees. A 90-degree triangle is called a right triangle. So you just identify it as one of these kinds of triangles. It's a right triangle. Also, you can ask the question, well, I guess the lengths do help you because you can answer what kind of triangle it is relative to the sides. And because all 3 sides have different lengths, it is also a scalene triangle. So it has 2 answers. It's a right scalene triangle. So I guess we can use the lengths. I was going to use that to prove it's 90 degrees, but they wanted to use it to prove that it's not either one of these 2. Which it can't be one of those anyway, because if you have 90 degrees, it's not one of these 2. No, that's not true. There is one isosceles triangle. That would be 90, and those would be 45. So there's one isosceles triangle. Yeah, I don't know what it's called. It's interesting. Okay, so this one is, as far as we have 2 sides that have the same length, so that means it's isosceles, and all the angles are less than 90 degrees. So because of those 2 facts, it is an acute isosceles triangle. Acute because they're less than 90 degrees, and isosceles, 2 sides equal. Try to slow down there, just in case. So here we have one of those interesting 30, 60, 90 triangles that you might remember from geometry. We don't really need to know that to answer the question. It is a right triangle, and again, the angles, the sides, we have 3 different length sides. So just like the original problem, it is a right scalene triangle. I think the first one was a right triangle too, wasn't it? Yeah. Okay, so that's pretty much, right now we're just identifying the kinds of triangles. In section 3, we'll be talking about how the angles of a triangle relate to each other, and that's the most important thing. Here's a list of, and it's in your book, so just follow along here. So we talked about the kinds of triangles based on the number of the angles and the side relationship between the sides lengths. So in quadrilateral, you have just a general quadrilateral. One kind of quadrilateral is a trapezoid. So a trapezoid has 2 parallel sides. These sides don't have to be equal to each other. The angles don't have to be equal to each other. The only requirement is that this 2 of the sides are parallel to each other. That's the only requirement. So I could draw, as an example, another example of a trapezoid would be something like this. So these 2 sides are parallel to each other, but there's no symmetry to it. This one looks kind of like it has some symmetry, and you don't have to have symmetry to be a trapezoid. A parallelogram has the opposite sides parallel to each other. Now in that case, there is some relationship. This angle is going to be equal to that angle is going to be equal to that angle. We'll talk more about that later. Then if you take this parallelogram and you make them so that these sides are parallel to the adjacent sides, and if one side is perpendicular to the adjacent side, then all of the sides have to be perpendicular to their adjacent sides. And so you get a rectangle, and the length of the sides doesn't have to be equal. The special case of a rectangle where all sides are equal to each other is called a square, which everybody knows what a square is. And the other special case is if you have all 4 sides equal to each other, but not a 90-degree angle. That's called a rhombus. That's the thing that we forget about. So a rhombus is a parallelogram with all 4 sides equal to each other. A rectangle is a parallelogram with right angles between adjacent sides. A square is a rectangle with all 4 sides equal to each other. So those are the different kinds of parallelograms, or quadrilaterals. Oh, actually, there's some good stuff here. So now these are the important things. So we'll spend a little more time on this. So the rule says the sum of the measures of the interior angles of any triangle is 180 degrees. So that means if you know 2 angles for a triangle, you automatically can calculate the 3rd angle. So it's kind of like supplementary, except you're going to subtract 2 angles, the measure of 2 angles instead of the measure of 1 angle. So if this angle is 40 degrees and this angle is 70 degrees, what is the angle here? Question mark. We'll call that B. So the measure of angle B is equal to 180 minus the sum of the other 2 angles. So if you get 180 minus 110, the angle is 70 degrees. So that's the unknown angle. I think you can prove this. I haven't thought about this before, but I think you can prove it by, I was telling you that sometimes you can, let me just take this triangle here, see if I can prove this or not. So in this case, I don't have parallel lines that are transversal, but if I do if I put a transversal in there that is parallel to the bottom side, Let's see if we can figure this out. So what we know is we know this angle is 40 degrees, and we know this one is 70 degrees. So if we ignore this line right now, we've got two parallel lines in the transversal. So this angle, which is a small angle relative to this transversal, and this angle, which is a small angle relative to transversal, is that's 40 degrees. So that angle is 40 degrees. They're corresponding angles. And you could do the same thing up here if you extend this line. This is the corresponding angle here is 70 degrees because you've got this transversal and these two parallel lines. Because this is a straight line, we know that some of these three angles have to be 180. That means this middle angle has to be, that's 110, so this is 70, right? That's also 70 degrees. So I'm just using the fact you've got a straight angle. And they're supplementary. Three angles are supplementary to each other. And then then what you would do is you would say, well, I've got this line I've got vertical angles here. I've got more than two lines intersecting, so I've actually got 6 angles. But the angles opposite each other, even with more than 2 lines intersecting, are equal to each other. So this angle here is going to be matched up with this angle right straight across. So this one's 40 degrees. Likewise, this angle here is matched by the angle completely opposite, which is that one right here, so that's 70 degrees. And this angle is vertical angle relative to this angle, so this one's 70 degrees as well. So there we go. So we finally got the answer. So you can see by using parallel lines and transversals, straight lines, straight angles, we proved that this is 70 degrees, and you could do the same thing with the general angle. Here I did it with a specific angle. But that's how this is proven, is to create this parallel line that's not in the original problem, but it allows me to then use stuff I know about parallel lines and transversals and vertical angles. You don't need to know how to do that. I'll just show you how you do that kind of thing. So here's a problem like we've had before. You're just trying to create a algebraic expression that uses the rule that we just said. The rule says the sum of the interior angles of a triangle add up to 180. So they're not equal to each other. It's not an equilateral triangle. So all we have to do to create the algebraic equation is to take the algebraic representations for each angle. So these are the measures of the 3 angles. And the measures add up to 180 degrees. That's the rule. So once we've applied the rule, then the rest is algebra. So we'll take 1x plus 1x plus 10x. We get 12x. And then we add the 15 plus 5 is 20. Minus 20 is 0. So I get 0. Right-hand side stays the same. I can drop the 0. And x is equal to 15, I think, right? 180 divided by 12 is 15. Okay, so x is 15, but that's not the answer. In this case, we have 3 answers. We have x plus 15, which would be 30 degrees. We have x plus 5, which would be 20 degrees. And we have 10x. 10 times 15 is 150, minus 20, 130 degrees. So you just plug x back in. And these added up should equal 180, which they do. This plus that equals 180. So this is really important, okay? Very important. If you take pre-calculus, you'll use this when you get to learning the law of sines and cosines. You always use that to help you out. Okay, what time do we got here? 2:05. Okay. Then you have a triangle. If you extend the sides of the triangle, you have these what we call exterior angles. So 2 is the interior angle. If you extend this side out you get 5, which is the exterior angle. And you can see they don't show it on here, but we could extend this side as well. If you extend the sides, you just get two lines intersecting. So we just get a lot of lines intersecting. So you can see that, you know, if this is angle 5 measure, this is going to be 5. These aren't the numbers, these just are representing the angles. So again, what you get here is you get vertical angles. These are all just vertical angles relative to each other. And what the rule says is the measure of the exterior angle, here, 5, is equal to the sum of the measures of the two interior opposite angles. So this is an interior angle, this is an interior angle, this is an interior angle. These are opposite this angle. So this opposite this angle are these two angles. So the two angles that are opposite this exterior angle are this one and that one. So what that would mean is that the measure of angle 5 is equal to the sum of the measures of the angles opposite. And that applies to any of the exterior angles. Now you could prove this the same way, because this plus that equals 180, and this plus that equals 180. So let's show you how you prove it. So from the previous law, angle 1, the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 equals 180 degrees. So that's the law about triangles. These two angles are supplements of each other. So I know that angle 2 plus angle 5, the measures, equal 180 degrees. Well, if these are both equal to 180 degrees, they're equal to each other. If the right-hand sides are equal to each other, then the left-hand sides are equal to each other. You get that. Notice I have angle 2 and angle 2. I can cancel those out. And so what it says is the measure of angle 1 plus the measure of angle 3 is equal to the measure of angle 5, which is the rule that we had there. So again, it's not super difficult to figure it out. We're using the sum of the angles in a triangle equal 180, and the exterior angle is supplemental to its corresponding interior angle. So in this case, we look at this and we say, oh, there's an exterior angle. Here are the three interior angles. Instead of saying, well, I could figure this angle out because I know they both add up to 180, I say, well, there's this rule that says the exterior angle is equal to the sum of the two interior angles. So in this case, they're equal to each other and not 180 degrees. So, so what we do is we say 26x, which is the exterior angle, is equal to the measure of one of the opposite interior angles and the measure of the second opposite interior angles. And then we have our algebraic equation, which we can solve. There's a lot of x stuff here, so so we'll have 10x plus 13x is 23x. And then we subtract 23x from both sides to solve for the x term. Divide both sides by 3. We get x equals 5. And then we go back and plug it in. So 13 times 5 is 65 degrees. 10 times 5 plus 15 is 65 degrees. And 26x is going to be the sum of those two. So that's going to be 130 degrees. So the sum of the two opposite interior angles is equal to the exterior angle. So actually, those 3 or 4 rules can allow us to go back and solve that really complicated drawing with all those angles that are, some of the anterior angles of the triangle is 180. We don't even need that last one because that's using previous stuff really. Some of the interior angles of triangle equal 180. Vertical angles are equal to each other. Supplemental angles add up to 180 degrees. That's all you need to know. You just have to figure out how to reason your way through it. And we'll do one in class, at least one in class. But you guys, I'll work it, and then I'll give you one to work, and we'll work through it together. They talk about circles in this chapter. Again, it's mostly just to introduce terminology. So we are going to talk about that in a second. So a circle is the set of points in a plane, each of which is the same distance from the fixed point. So here's our fixed point. The points on the circle are, it's a set of points. So all these points put together create the illusion of a constant line. And, well, maybe not illusion, but, and each point here is the same distance from the center point. That's the circle. That's the mathematical description of a circle. I'm sure anybody could tell me what a circle looks like. Now there's all these other things associated with circles. I do put something like this on the tests, so make sure you're able to, what you have to do is be able to identify the line segments and the lines and the rays that correspond to these definitions. So what I have is these different things, and we'll talk about what they are, and we'll use these letters to represent these all these different things. So we're going to go through them. We'll start on them today. We're almost done here. It's almost 2:15. Made it through another week. So the center, okay, that's not too difficult. The center is a point. So we would just say O is the center. Right? That's the point where all the other points on the circle are equal distance from. Now the radius is, you think of radius as being a number, like 5 feet or 2 inches. But the radius is actually a line segment. And there's more than one. So the radius is the line segment from the center to a point on the circle. So I could represent the line segment as line segment 0 or OP. So those are the 2 points, and then I put a line over top of it to show that it's a line segment. Also, OQ would also be a radius. And OR would also be a radius. Because the order does not make difference, we could also change the order. You know, we could have, well, actually, maybe we don't. I think we want to start from the center of the circle. So we always have the center as the first letter, and the radius, the point on the circle, as the second letter. So that's what those are. This line from here to here, that line from there to there, that line from there. That's the radius. Now a chord is the line segment connecting 2 points on the circle. So there are an infinite number of them, but in our case there is only, well, there actually are a couple. The one that's most evident is the line segment PQ. But one that you may not think about would be PR. That's a special chord. So that's going from here to here, and it goes straight through the center. But it's still a chord. That same line segment, PR, is also what we call the diameter. And that could be either way. We could have RP or PR. So the diameter is the line segment that goes from one side of a circle through the radius, through the center to the other side. Okay, we'll stop there for now. So the homework that I assigned today is due next Wednesday. And let me make sure I got everybody I don't think anybody came in late, except Justin, but I got Justin.